Sheffield in 1740, the year when Benjamin Huntsman invented the crucible method of steel making. Already, as the home of cutlery, Sheffield had centuries of tradition in the hand forging of iron blades. In 1774, we find the first record of the men who laid the foundations of the present company. John Marshall, cast and blister steelmaker and watch steel forger; George Naylor, penknife cutler, making knives such as these. Over the years, Marshall expanded his premises and occupied 2 water-powered forges and tilts on the River Don. Here, cast steel ingots were forged into suitable shapes for making cutting tools, razors, knives, and other products. In 1829, George Naylor's grandson entered into partnership with Edward Vickers, who previously had operated a cutlery grinding business. The partners also took over Marshall Steel Works with forging and tilting plant on the River Don. With the development of steam engines, forges were no longer dependent upon running water for power. Beam engines were used to drive the tilt hammers. One of the firms taking advantage of these developments was Johnson Camel and Company, established in 1837 as steel and file manufacturers. In 1845, Johnson Camel moved to a new site, Cyclops Works, with a special railway materials department operating steam-driven helves or nose hammers. In the same year, James Naismith, the Manchester engineer, designed a self-acting steam hammer, this being his original scale model, which is now in the Kensington Science Museum. These hammers brought about a revolution in the design and production of forgings, and opened up new horizons for designers of many kinds of heavy engineering equipment. Until the 1860s, the usual method of making crankshafts and propeller shafts was to hammer weld wrought iron into slabs. The forging was then built up layer by layer under the hammer. Greatly increased production of crucible steel led to the casting of large ingots, which proved to be particularly suitable for ordnance forgings. This old print shows the busy scene when a large ingot was being teamed. By the early 1860s, production of even larger ingots was made possible by the introduction at Vickers and Camel's works of Siemens open-hearth steel furnaces, some of the first in Great Britain. During this period, both firms enlarged their premises. Mills and hammers were installed for making tires, axles, and other railway forgings, shafts and crankshafts for paddle steamers. Although Charles Camel installed the world's first forging press with a rating of 1250 tons, Sir Joseph Whitworth was the first man fully to appreciate and develop hydraulic presses for forging the ingots which had become too large to be worked under the hammers. Century, the demand for armored ships was growing, calling for closer cooperation between the builders and the steel manufacturers. Camel amalgamated with Laird Brothers, shipbuilders of Birkenhead; Armstrongs of Newcastle amalgamated with Whitworths, and Vickers took over the Barrow Shipbuilding Company. There followed a period of great expansion. Rapid progress in engineering designs was made possible by developments in the field of metallurgy and introduction of new alloy steels. In the period 1928-29, the steel interests of Vickers and Armstrong Whitworth, already grouped as Vickers Armstrongs, were amalgamated with those of Camel Laird to form English Steel Corporation Limited. The works of the company in Sheffield alone cover a total area of 155 acres, and provide employment for more than 10,000 people. In the field of forging, one of its subsidiaries, English Steel Forge and Engineering Corporation, maintains the proud traditions of its original founders, and is one of the largest producers of steel forgings in the world. Steel, backbone of the nation's economy, plays a vital part in the construction of all types of machinery and heavy engineering projects. Most of the important components are made of carbon or alloy steels produced as forgings or castings. Castings can be produced in complicated shapes, made by the pouring of liquid steel direct into a sand mold. Parts which are subjected to higher stresses, however, demand the improved physical characteristics which are obtained by forging. Forgings are made by pressing or hammering an ingot to the approximate shape of the finished component, at the same time breaking down the coarse crystalline structure which remains when an ingot has solidified. One of the simplest examples of this is the drawing out of an ingot to a plain round bar. The designs of the majority of forgings are more complicated, calling for variations in diameter or section. Solid forgings are made from the body portion only of the ingot. The large tapered end, known as the feeder head, which provided a reservoir of liquid steel to feed the ingot during solidification, is later discarded. Ingots from 30 hundredweights up to 300 tons are produced by the pouring of liquid steel into cast iron molds. Here, the mold has been prepared for the casting of a huge 275-ton ingot. Steel of special quality appropriate to the product has been melted in 3 Siemens acid open hearth furnaces, each containing over 90 tons. This synchronization calls for teamwork and skill of the highest order, from the charging of the furnaces to the teaming into the mold. The ladle, which contains the first charge, is positioned over the mold. In order to ensure smooth flow of steel into the mold, the initial pouring is done through a trough. When the well of the mold has been filled, the trough is removed and the ladle is lowered onto the staging. The crane is freed and travels along the casting bay to make way for the ladle from the second furnace, which is now being tapped. Once started, the pouring of the ingot cannot be stopped, and the second ladle, suspended by overhead crane, arrives over the first ladle to keep up an uninterrupted flow of steel. Steel is now being tapped from a third furnace into a third ladle. This will shortly replace the second ladle. The ingot mold revolves during the whole of the pouring operation. After nearly 2 days, the ingot has solidified and has cooled sufficiently for the mold to be stripped off safely. A special beam and lifting frame are necessary for raising these massive 275-ton ingots from the casting pit. The ingot, while still hot, goes to the treatment furnace, where it is annealed and cooled down to atmospheric temperature. This annealing process, which has taken several weeks, limits stresses which would otherwise be set up during cooling of so large a mass and which might cause cracking. Selection of the most suitable type and size of ingot for any particular job involves careful planning and calculation. As an instance, this forging for a marine intermediate shaft has been made from an ingot similar to the one which lies alongside. We will now go into the forge and see how such a shaft is made. An ingot has been heated to a grade in a gas-fired furnace. For lifting and manipulation, a hollow tube is fitted onto the head of the ingot. This is called a porta bar and acts also as a counterbalance. The first forging operation is known as cogging and produces a round billet. Let us see how a press operates. It is driven by electro-hydraulic pumps seen on the left. When the driver operates the control valve, pressure is fed to the cylinders in the top of the press, forcing down the crosshead and squeezing the hot steel between the tools. The driver then pulls his lever to another position, which operates a separate feed to raise the crosshead. Work continues until the diameter corresponds to that of the coupling flanges of the shaft. Careful calculation determines the position of the flanges. The actual marking out calls for considerable skill on the part of the forgeman. Before further work can be continued, the partly forged shaft has to be reheated. The final stage of production involves the drawing out in length of the main section of the shaft between the flanges. Another example of shafting is this very large turbine alternator shaft for a hydroelectric scheme, here being rough machined after heat treatment. Similar forging technique is used for such items as rolls, propeller shafts, drill collars, pipe molds, and turbine rotors. Rotors are vital components in turbo alternator units for the generating of electricity. There are two types: the steam turbine rotor, which provides the motive power, the alternator rotor, which is part of the electrical generator and is here being slotted before the fitting of the coils. Great care is given to the heating of the special steels from which forgings such as rotors are made. After cogging to the major diameter, the forging has been reheated and one end is now being forged to shape. After completion of forging, the rotor is charged into a heat treatment furnace. The entire treatment cycle is both lengthy and complicated, being determined by the type of steel used and the size of the forging. A view inside the furnace shows this and another rotor at a temperature of 700 degrees centigrade. The forging has been heated finally to a temperature of 920 degrees centigrade in order to refine the structure of the steel. At this stage it is being withdrawn for air hardening. The rotor is placed on rollers to facilitate rotation and ensure uniform cooling conditions. This air hardening, or normalizing, is followed by a tempering and stress-relieving treatment. The rotor is now transferred to a machine shop almost a quarter of a mile long, which houses one of the largest and finest assemblies of heavy machine tools in the world. The first machining to shape removes forging irregularities and also prepares the surface for examination. Rigorous metallurgical examination is carried out at all stages of manufacture. The ultrasonic flaw detector, a type of echo sounder, is used to confirm internal soundness. Sulfur prints are taken to confirm freedom from harmful segregation of impurities. Manufacturing processes vary according to the type of rotor. In order to develop the desired properties, some rotors have to be oil hardened and tempered. This particular turbine rotor has been heated in a vertical electric furnace to a temperature of 920 degrees centigrade to refine the grain structure. Quenching in oil develops a high tensile strength. After several hours, the rotor is withdrawn from the oil tank. It is then recharged into the furnace for tempering at 640 degrees centigrade. This process relieves the stresses set up during quenching, reduces the tensile strength to the desired level, and improves the ductility and toughness of the steel. After heat treatment, test sections are removed from body and shaft ends. By trepanning, a hole is machined through the entire length of the body of the forging. This enables the core to be removed intact for examination and testing. To determine tensile properties and ductility, test pieces from all specified positions are turned to standard diameters and lengths. The actual testing is carried out in the presence of an inspector appointed by the customer. Of the proof stress. Loading is now continued, maximum stress being indicated on the dial. The extension of the test piece and reduction of area at fracture indicate the ductility of the material. Impact tests may be made to determine resistance to shock. Further extensive machining to shape includes gashing to form the discs into which the turbine blades will be keyed. A final stress-relieving treatment will follow. The bore must be completely free from defects. After the final boring operation, every inch of the surface is inspected minutely with the aid of a borescope. Other types of turbine rotors are built up by fitting separate discs onto a central shaft. For the production of these discs, an ingot is first forged to a round bloom from which individual blocks are cut. These blocks are then forged at right angles to the original ingot axis. This upsetting operation changes the grain flow as shown by the lines in the diagram. It ensures the best properties in relation to the stresses to be encountered under service conditions. Movable shoes fitted to the rotating press tool enable various sizes of discs to be produced. These shoes also permit varying thicknesses to be forged on the same disc. Similar upsetting process is used in the manufacture of gear blanks, smaller blanks being produced under hammers, the larger under presses. This traditional method of hammering gear blanks is a fine example of skill and organized teamwork. It is, however, being replaced steadily by techniques employing mechanical handling.
Great
skill is required also in the forging of many intricate shapes, such as these undercarriage, airframe, and engine components. A specialized method of forging designed to give uninterrupted grain flow is the continuous grain flow process for forging crankshafts. This shaft has been pressed, one throw at a time, from a bar identical with the one which lies alongside. A section of one of the throws of a CGF crank has been etched to show how the grain flow follows the contour of the forging. The length of bar to be worked is heated to forging temperature in a specially designed furnace. The partly forged crank is placed in the lower locating and forming dies, which are mounted on the sliding table of a 6,000-ton press. The crosshead of the press, carrying the top tools, commences its downward stroke. The bar is gripped at 3 points. The press continues its downward stroke, forming a single throw. Although one throw only is forged at a time, we show this interesting forming operation again. As each throw is completed, the crank is returned to the furnace for the heating of another section. The CGF, continuous grain flow method of forging diesel engine crankshafts to close tolerances, effects saving both in material and machining. British diesel engines play a major part in the shipbuilding programs of the world. This working model of a Doxford diesel engine illustrates the complicated mechanism of the unit, which employs a great variety of forgings. In addition to parts for the built-up crankshaft, there are side and center connecting rods, piston heads, and piston rods. This lathe is completing the machining of one half of a crankshaft for a 4-cylinder engine after assembly from 9 components. A model of 2 throws of a 6-cylinder crankshaft shows the main webs, the crank pins, a journal with integral webs and pins at 120 degrees. These journals are usually forged in pairs from one ingot. The ingot has been cogged and the web sections set out. After reheating, further forging produces the smaller crank pin sections. In the machine shop, the partly made forging is carefully checked and marked out. Rough machining of the main journals at this stage positions them relative to the webs and crank pins. Back in the forge, the pair of journals has been reheated in preparation for twisting. The center pin section is held under the press. A large spanner, manipulated by an overhead traveling crane, is then fitted to the end pin section of the crank. With one web and pin section held stationary by the press, the other web and pin are rotated about the machine journal. Maximum leverage during the whole operation is obtained by the use of a ratchet on the head of the spanner. The forgeman makes a final check of the positioning of the pins at 120 degrees to one another. After an intermediate heat treatment, surplus material is removed by oxyacetylene cutting, considerably reducing subsequent machining. In most instances, the two 120-degree journals are maintained as one forging until fully rough machined. After separation, the two pieces receive their final heat treatment. We have so far described solid forgings, but some forgings are made hollow, such as the outer rim of this wheel for use in a ship's reduction gearing. A gear wheel rim is made by progressively reducing the wall thickness of a hollow billet, thus increasing the diameter of the forging. Two stands built up on the press bed support a becking bar which passes through the hole in the billet. The press squeezes the hot steel against the bar. As the bore grows in diameter, the ring can be transferred to larger sections of the becking bar. With rings over 12 feet in diameter, it is usual to reheat before the final forging operation. After heat treatment, the gear wheel rim is rough machined before dispatch for gear cutting. Another example of hollow forging is a boiler drum. Many of the world's power stations rely on high-pressure turbines. The steam is generated in boilers which may operate at pressures in excess of 2,000 pounds per square inch. The most satisfactory method of manufacturing a high-pressure boiler drum is to forge it in one piece with no welded or riveted joints. At present, the largest drums require ingots weighing up to 300 tons. The first operation on the cold ingot is to part off the top and bottom discards, consisting of the feeder head and the well. The core of the ingot is then removed by trepanning. Two hollow bars, which are fed from each end of the machine, carry the cutting tools. These are set in such a way as to produce chips small enough to be washed through the clearance between the outside of the boring bar and the hole which is being cut. In the forge, the billet is heated to forging temperature. This forging press is the largest of its type in Great Britain. The first operation is to enlarge the inside diameter of the billet. To do this, the press squeezes the hot steel against the bar which passes through the hole in the billet. After the first sequence of forging, the billet has been reheated and is now ready to be drawn out in length. The tool, known as a mandrel, which passes through the forging, maintains the size of the bore during this and all subsequent drawing operations. For so large a job, several reheats are necessary. One end already completed, the forging is turned about, the second end reheated, and drawing out is continued. Forging completed, the drum is transported to the heat treatment department. The forging is now normalized to refine the structure and is then tempered to relieve the stresses set up during normalizing. In the machine shop, rough turning is carried out in one of the largest lathes in the world, capable of removing more than 4 tons of steel turnings per hour. The inside of the forging is machined in a double-ended borer. Tool bits are clamped in a row in the boring head, the last of the set being adjusted to give a fine cut and a smooth finish. The ends of the drum must now be forged to shape. After being heated to forging temperature, one end is being shaped under the press using specially designed tools and dies. further heats are required completely to form the end. Forming completed, the first end has been normalized and tempered. The other end is now being heated prior to forging. Back in the machine shop, there follows a sequence of turning, milling, and drilling operations. The milling of the manhole in each end of the drum is controlled by an electronic device. Special equipment is used for machining the internal radius of the ends. The cutting tool, working inside the drum, is controlled by an arrangement of levers. The lathe, which is used to finish machine the outer surface, is also fitted with electronic controls for turning the radius of the ends. After careful marking out, the holes for nozzles and stub tubes are drilled. These nozzles and stub tubes, which will provide connections for water and steam and for various gauges and fitments, are welded into position. Local stress relieving is carried out after the welding of each fitment. When all welding is completed, the entire drum is stress relieved in a furnace. With manhole covers fitted and holes in the nozzles temporarily plugged, the drum is ready to be tested under hydraulic pressure. The test pressure is almost 50% higher than that encountered under working conditions. Accurate checks are made to record any signs of distortion. Jigs are used to ensure absolute accuracy in the spacing of tube holes. The boiler can then be erected on site without previous assembly. The drum is now ready for dispatch, a masterpiece of heavy engineering. Reaction vessels for the chemical and oil industries, where enormous pressure and high temperatures are encountered, can only be made satisfactorily by forging. Accurate and careful machining of all the components is essential. Many vessels must be made from highly alloyed steel to its gas attack, thermal creep, and corrosion. Wherever strength is needed, the world over, ESC forgings are withstanding the test of time. Strength is needed, the world over, ESC forgings are withstanding the test of time.